Hello all, welcome to my channel. Uh, this is a new video. In this video, we will be talking about a very common concept in Spark, which is shuffle. And this is part of five video series that I will be doing. This that will deal with shuffle, spill, skew, serialization, and storage. So basically, we will discuss the five painful S of Spark job. So let's get started with shuffle. Okay, so to understand what a shuffle is in Spark, uh, we will have to understand how Spark does store data. So Spark stores data in partitions as a data frame, which is logical layer on top of RDDs, which are distributed across nodes, and one partition of Spark is processed by one executor. So that's the basic concept. What happens during a shuffle is basically it's a process of redistributing the data across nodes or across executors. And the reason it is being done is to calculate something. So there are in Spark there are two types of transformation. One is wide transformation, other one is narrow transformations. Narrow transformations are those actions, those so not actions, those modification to data which does not result or in an sorry not result I will say it does not require knowing other rows. For example, let's say we want to increment the value of a column in one data frame. That does not it doesn't have to know what is the value in some different row. But there are certain transformations which require us to know a set of rows or rows with which we can combine things into. For example, let's say we do a group by operation where we want to know the total number of sales done by a store. So we will be doing a group by based on the store ID. But when we do this group by, all the keys, all the rows which belong to the same stores should be processed by one particular executor. That's when this data has to be moved from one particular executor to other executor, and that's the process is called a shuffle. This is what it is documented in here, and then this is how it looks like internally. So this is stage one and this is stage two. So each shuffle will create it will not create, it will sit in as a boundary between two stages. And the example that I was discussing, let's say we have a map task. It's coming from map and reduce, but we can say that there was a task which happened in, let's say, executor one, which was processing partition one. It had five rows, one which each keys being A, B, C, D, sorry, four rows, A, B, C, Ds. Other map task also had the similar keys grouping. It's the other values can be different. Uh, Basically, what I want to say is the column on which or the values on which the grouping will happen is A, B, C, D. Same with partition three. Now, what will happen? Let's say we want to do some uh, aggregation based on this key. So all the tasks which are supposed to be of partition A or grouping column A should come to this particular executor, right? So if you see what it is doing is it will go and fetch the records from executor 1. It will also go and fetch the record A from records with having a key A from partition 2, same with partition 3. So if you see how many, like there are multiple crisscross connections happening, right? Each of these is fetching data from each of the other executors because the data is distributed in such a way. This process is called a shuffle. So there are two major things that we see here is there is a lot of connections that is happening. Each executor is talking to the executor, and the other one is there is a data movement happening. So data is moving from one executor to other executor over a network. So we see a network IO. There are other things like serialization, deserialization. If the partitions are getting written to disk, that's where the serialization will happen, and then it will be persisted to disk. Then the other executor will read it from the disk. During that, after reading it, it will deserialize it and do the processing of that. So this is a challenge. And if we see for any job, let's say if the job is running and if we want to see whether there any shuffle is happening or not, you will see nodes called exchange. So all those nodes which have exchange, you will see data is coming from some other stage. So this was stage 0, this was stage 1, and data from stage 1 and stage 2 are being, sorry, stage 0 and stage 1 are being used by stage 2, and then stage 3 also leverages something. So this flow, if you see, the data is moving from here to here, here to here, here to here. So this is combined uh, n- shuffle operations that we can see in the history server. We can look at the history server or the live UI in the query plan, and we will see, oh, sorry, a DAG view, and we can see whether this shuffle is happening or not. So this is the whole phenomena, and now we will talk about how these shuffles are executed inside the Spark paradigm. So each shuffle has two sides. One is the shuffle write side, and another one is the shuffle read side. And in the shuffle map, where you can simply say it is a producer where the data is, and this is the side where the data needs to be present, or it is required in this side. So the how it happens is shuffle. There is a shuffle write processor in Spark, which will write the data of the shuffle to disk with do two things. One is shuffle data and as well as shuffle index. Why this index is needed? Because the faster lookup. So if let's say executor wants to know whether I want this particular data, is it present in this? If he has to see all the data that is written, it will be slow. So it creates a shuffle index as well, and that index it simply said, okay, you want this data, go and read from this site. So that way the index is stored. And the other one is the read side. What it does, it will fetch the shuffle block from here, which is there is a process called shuffle reader which fetches that blocks, and then it will create an RDD, and then it processes that as it is. So this is a high level overview, and if we dig deep in how the shuffle write process happens, so this is a host. Host has executors. Executors under that, inside the executors, we have the shuffle map process. So the shuffle writer, before writing, it does an external sort and then creates an index. Then it first writes it to the memory buffer, and then if once the memory buffer is full, then it will write it to disk as a spill file, and that data file, uh, based on these, it creates a data file, and then there is an index file as well that gets written to the disk. uh, on the reader side, what it will do, it will talk to shuffle read, will talk to the service or executor in this case, and it will say, boss, I want this particular data. So it will talk to this and it will say, okay, there is an index file which says where is partition 1 located, where is partition 2 located. So it will read those partitions. Partition, this is not data frame partition, this is uh, data partition per se. So that partition is read by this shuffle read process, and if that memory gets filled in here, memory buffer gets filled, it will again write it to disk. So that's why if you see there are multiple times disk read and writes are happening. So here, if you see in this case, data was in memory, then it was written to disk, then from disk it was read to memory, and then again it was written to disk. So that is something uh, it's very slow. That's why whenever we see a shuffle process gets involved, uh, the jobs will run slow. So there are certain configurations that we can use to make this uh, shuffle process faster. One is that we can compress the data while writing. We can also compress the spill that is happening. We can also decide the size of the buffer, how much size we want for the buffer. We can decide the compression algorithms like codec, so it can be ZSTD, LG4, or GGIP. GGIP is generally not used, but Snappy or other configurations that we want. So those codecs we can define in here. So this this is how the shuffle process happens in Spark, and why it is slow and why it is a resource intensive work. We have gone through that. So how this shuffle can be improved is, first of all, we can reduce the amount of data that needs to be exchanged. So that is one way. There are other implementations of this. So this whole shuffle process is an extensible module in Spark. We can write our own custom shuffle managers. So there is a setting called Spark Shuffle Manager, which decides what shuffle manager, which class will be loaded to handle the shuffle, and that we can define our own system. And so there are certain external uh, mechanisms like that can be used. For example, this is one implementation of the Shuffle Manager by Uber. No, sorry, I don't think this is Uber. This is LinkedIn. So this is Magnet, which the LinkedIn's team built, and then later on it was donated to Spark 3.2. So how this works, external shuffle service works in Spark, is that on each of the node there is a separate process that keeps on running as an which we call it shuffle external shuffle service, which keeps on running on each of the nodes of the Spark cluster, uh, and that particular service is responsible for talking or exchanging the data. So now earlier what was happening, each executor was trying to talk to the other executor. Now it is not happening that way. The executor will talk to the shuffle manager, and the shuffle manager will return the response. So we have reduced certain number of executors that were so a certain number of connections that were required earlier. But there is one more thing. If the node goes away, there is no way we can recover that, because that node shuffle manager is node scoped. So that shuffle service will lose any data that was there, and the process has to recompute. But still, it is better than the earlier one where executor was hosting the data. Here, if you see, the executor had the control of on the local disk, and that used to maintain who will access and who needs that data. That changes with external shuffle service of Spark slightly in a sense. The ownership now moves away from executor to the shuffle manager, and if the executor is lost, still we will be able to get data because shuffle manager knows that data. So that was at execute node level. So we have elevated the error, what you call error scope from executor to node. But that also is something which is not fully optimal for large clusters, or in cloud environments. Node coming up and going away is certain common phenomena. Like for example, if we are using EMR, and if we are, let's say, working with task nodes on Spot, uh, uh, with a spot nodes which come and go based on the spot pricing. If that node goes away, the no all the shuffle all the executors that has written to that particular node shuffle manager will be lost as well. So few companies have implemented external shuffle services, what we call is so all together on the same cluster where Spark is running, or in a different cluster which has connectivity to the Spark cluster, there will be a different service altogether running, which job is to handle this shuffle process. So what we are basically this implementation says is that all the nodes, all the executors which have the output, they will write their shuffle output to a centralized cluster, which in turn will handle. So executors won't talk to each other. executors and nodes won't talk to each other. Executors will simply say that for this particular my task, this is the partition, this is the data file, this is the index file that I want to persist remotely, and that remote cluster will take that. And if some other executor needs it, it will contact that external shuffle service and then take the data and process the data. So there are multiple implementations, like there was Magnet from LinkedIn, which has contributed back to 3.2 Spark. Then we had Celebon. So not Celebon, it is Calebon. It's pronounced as K. So Calebon is another open source solution that now it is not incubating. I think it's matured enough. So Calebon is an external service. Then there was a Juice from Uber, Refill and Costco from Facebook, and there is one more from, I think it is Unifil from Tencent or Alibaba Cloud. So there is one more shuffle service which is there out there in the market. All those are open source. There are certain other remote shuffle services as well. For example, AWS also has a shuffle storage plugin that uses S3 as their shuffle storage, and that is available for consumption. Splash is there, then there's an OAP shuffle as well. So these are remote shuffle services. I think all of these are backed by object storage. These are not backed by object storage. These are backed by the node's local disk on which this services are running. So yeah, these are some external services. We will go. I am planning to create a separate blog on that Spark external shuffle services. That we will create a video out of it as well. So yes, in short, Shuffle is a process of distributing data across nodes or executors in Spark, and that is required in cases where we need aggregate data from different rows. And there are some challenges with it. One challenge is that loss of executors will cause recomputation. So that is one. Other one is because there is a lot of I/O involved, disk I/O, so the performance goes down. And let's say on a same node, let's say there are five executors running, and two are from one job and two are from other job, some different job, and those jobs are writing too many shuffle data, but my job is not writing that much of shuffle data. But still, because the disk is shared, the IO is shared, if that disk degrades, the performance of the other job also degrades. That's what the noisy neighbor scenario happens. Also, scalability is an issue because shuffle can delay the process. And let's say if we have executors defined and the static executors are defined, and at that time, let's say shuffle is taking too much of time, although we are not doing, the executors are might not be doing anything, they are just sitting idle for waiting for that shuffle to be available. So that again becomes a skill challenge that we can't bypass directly. There is one more extra challenge with dynamic resource allocation, because in the DRA, executors come and go as soon as they are done with the job. But in those cases, if the shuffle is owned by the executors, that also can be lost. So we have to enable that, explicitly saying that okay, there is a shuffle service enabled, and we have dynamic location shuffle tracking needs to be enabled. Then only we can maintain the shuffle in a proper fashion if we have to work with dynamic resource allocation. So these are certain aspects of the shuffle. We have gone in this blog, we went through few things like how shuffle works, why we have M cross N kind of networking that happens, why there is stage boundary, and what are the challenges, internals, how it trades. So yeah, this blog pretty much covers all the intricacies of shuffle. Uh, Thanks for your time. If you like this video, do share it. Thanks.